work through the quiz review today, and then if we get done with this, then I'm going to just pick out the problems that we didn't get a chance to do from the packet. Again, your test is going, sorry, your quiz on Friday is going to cover L'Hopital's rule, particle motion. You'll have a problem like this where asking about these items that we went through yesterday, and then linear approximation, and then the rest of the quiz will be related rates. And again, here are the topics that we're responsible for as far as related rates go. This is on the back. This is page 4 of your review sheet. So Pythagorean theorem problems, area of right triangle, sphere, either volume or surface area. And the formulas we provided, if it's a sphere, cone, cylinder problem. We have 2 variations of similar triangles with cones and then with the shadow problem. Trig related rates, this is where you're gonna decide whether to use sine, cosine, or tangent to build your equation. And we'll do one of these in class today. And then we need to make sure we know just the basic formulas: Pythagorean theorem, area of circumference of a circle, area of a square, area of a triangle. Okay, SOHCAHTOA. So even though today is going to be the last day that we're going to devote a full class period to do quiz review, we still have a little bit of Wednesday and Thursday to do a little bit more quiz review. But tomorrow we're going to start Unit 5. And again, with Unit 5, I'm printing out just class copies for the notes packet, but you can also find the notes packet, the PDF, on my website, and I'll send that link out today to you so that you can, if you want to print one out, you can. But please bring like a spiral notebook so that you can take your notes in there, and then you can also do your homework in there as well if you don't want to print your own copy. Okay. So let's go to page 1, and let's just go through the problems that we haven't done. So yeah, go ahead and try 2, 3, and 4. 2 and 3 are limits. So L'Hopital's rule if possible, but number 4 is not limits. This is the derivative. So yeah, go ahead and try those, and then we can talk through them. The keys are also attached, so if you're working ahead, feel free to do that. It's the quiz review. Yeah. Yeah. 20 to 30. Great. So for 2 and 3, if you're jumping directly into L'Hopital's rule without showing me that that there's an indeterminate form, then you'll get a point taken off. So make sure that you're showing me your direct substitution steps before you apply L'Hopital's rule. So number 3 is a problem where after you do L'Hopital's rule, you're still getting a 0 over 0. So that means you can do L'Hopital's rule a second time. And that second time through will get you a real number, so we can stop there. Number 4 will just be quotient rule. We don't want to do L'Hopital's rule for 4 since it's not asking for a limit. It's a derivative problem. Okay, any questions? 2, 3, or 4? All right, let's do number 5 together. All right, number 5 says if the length of a rectangle is decreasing at a rate of 2 inches per minute, while its width is increasing by a rate of 2 inches per minute, which following must be true about the area of a rectangle. So we know that this is related rates because there's a time component with the derivative. So let's start off with building the area of a rectangle, length times width. And if we want to find the derivative with respect to time, we know we're going to be expecting dA dt, dL dt, dW dt. But at the same time, this is product rule here. So we got to go through a full product rule to build the derivative. So let's see what they give us here. They say that length of a rectangle is decreasing at a rate of 2 inches per minute. So we know that's referring to dL dt. It's going to be -2. Width is increasing at a rate of 2 inches per minute. So we know dW dt is a +2. Which of the following must be true about the area of the rectangle. So we're going to plug this into our variables and then just see what we have and see if we can just logically decide which answer could be true. So replacing dL dt with -2. So I get -2W plus 2L. Now, we don't know what W and L are, but hopefully we can decide which of these options will be the best fit. It says A is always increasing. That means dA dt is always positive. Is dA dt always positive? Right, depending on, remember, we can choose W and L to be any scenario. So if we can find a scenario that will cause something to be false, then we can eliminate that option, right? So it's not always increasing, right? If W is for some reason greater than L, then I'm getting a negative rate, and negative rate would be decreasing instead. So A is out. A is always decreasing. Well, we can create a scenario where L is greater than W. Then we can make it increasing. So this is not always decreasing. We're trying to find something that is foolproof, that no matter what the scenario is, there'll always be a true statement. A is increasing only when L is greater than W. So are we gonna get a positive dA dt whenever L is greater than W? Yes, right. So as long as, so in this case, we do have a scenario that is strong enough, or a condition that's strong enough that will make it this always a true statement, right? As long as, because they have the similar coefficients, one is positive and the other is negative. If L is greater than W, then 2L will be greater than 2W, and that will ensure a positive value. So this should be true, but let's just ensure that the other ones are false. A is increasing only when L is less than W. So when L is less than W, then all of a sudden this will become a greater negative than positive. So A will always be decreasing instead, which is not true for this statement. And then A remains constant. That means dA dt is going to be 0, which is not true, right? dA dt is only 0 if W and L are both 0. And that, that doesn't always have to be true, since W and L can be anything. So our answer choice is going to be C. All right, we worked through all of page 2. So let's go to page 3. This is a linear approximation problem. So again, with linear approximation, don't worry about the decimal. Okay, focus your attention on building that tangent line equation. So this is something that we've learned from previous unit, right? So find your order pair, find your derivative, find your slope, build your tangent line equation, and then your final step is inserting that 0.5n. So as you build your tangent line equation, you shouldn't need a calculator. We should be able to build our tangent line equation from exact values. Okay. So see if you can start this problem here on your own. Find your order pair from your function, build your derivative. What rule do we need to build the derivative here? Chain rule, yeah. Make sure you build derivative through chain rule, then plug in pi over 6 to get your tangent line equation. And if you get your tangent line equation, that's basically the majority of the problem. The final step is then you can plug in that 0.5. And even without a calculator, you can do it, because if you plug in 0.5 and leave your answer unsimplified, that's sufficient. That is also a sufficient value. Okay, so f of pi over 6, plug pi over 6 into the original function. I get 1 minus sine of pi over 6. Sine of pi over 6 is 1/2. 1 minus 1/2 is 1/2. 1/2 squared is 1/4. There's my y value for my order pair. F prime, outside times inside's derivative, 2 parentheses to the first power, multiplied by the inside's derivative. Replace all the x's with pi over 6. 1 minus pi over 6, sine of pi over 6 is 1 minus 1/2. Cosine of pi over 6 is negative, or root 3 over 2 with a negative in front. But there's my slope. There's my tangent line equation. And then you can plug 0.5 in for x. I do want to talk about how you can leave your answer in this form, and this is good to know, especially if it's a non-calculator section on the AP exam. This is how you would leave your answer, right? You don't want to worry about having to do anything further than this. As long as all your trig are resolved, all your numbers are a mess, but this is sufficient. Okay, is our linear approximation an over or underestimation? The big hint is the fact that it's concave up. So if the graph is concave up, my tangent line is always what? Under. Yeah. So no need to memorize it. If you just graphed a concave up graph, a graph that's opening up, and no matter where you put the tangent line, it's going to sit below the curve. So our tangent line approximation is going to be underestimated. Okay. Any questions? 7, A or B? Okay, let's do a cylinder problem together here. Cylindrical barrel with a diameter of 2 feet contains our collected rainwater. Rain drains out of the valve at the bottom of the barrel. So here, the water is going to be decreasing. The rate of height is modeled by dH dt equals negative 1/10 root h. So the height is decreasing as time passes. Volume of a cylinder is V equals pi r squared h. Find the rate of change of the volume of the water with respect to time when the height of the water is 4 feet, indicate units of measure. So again, even though cylinder formula looks like cones, it's an easier related rates problem because what do you know about the radius? It's a constant. So you can immediately get rid of the radius with a number, and you can do that before you even begin the problem. We can't do that with cones because the radius and the height are both changing. We need to go through similar triangles with cones, but with cylinders, we can immediately get rid of the radius or replace the radius. What's our radius? 1. Yeah, diameter is 2, so radius is 1. So this is now our new starting point. So our derivative should be a lot easier. No need for product rule, no need for similar triangles. We can go directly into our derivative. V becomes dv dt. Pi stays. H becomes dH dt. Make my substitution. And then to find dv dt, all I need is the h value. I do know that the h value at this moment in time is 4 feet. So plug in 4 in for h. Root 4 is 2. Negative 2 over 10 is negative 1/5 or negative pi over 5. And what's our unit? It's going to be, we need volume and time. So volume is in terms of what? 3-dimensional, yeah, cubic feet per second. Yeah. Okay, part B, when the height of the water is 3 feet, the rate of change of the height of water with respect to time, is it increasing or decreasing? So we know the rate of change of height is talking about dH dt, right? And we have a formula for dH dt, but it's asking to know if dH dt is increasing or decreasing. So this is not talking about dH dt. This is talking about what? Yes, it's asking for the derivative of dH dt, right? It's asking for the slope of dH dt. It's asking if is this rate increasing or decreasing? So we're going to have to move to our second derivative with respect to time. So let's write that out first. So dH dt. Okay, so derivative d2h over dt2. And here, I just go through power rule. Now, I am asking for a derivative with respect to time, so I still need to multiply it by what? Yeah, dH dt. Now, we know what dH dt is, right? dH dt is -1 root h, so I can get everything in terms of h, and then I can plug 3 in, and I can see if my second derivative is positive or negative. If I get a positive second derivative, I know that my rate is increasing. If I get a negative second derivative, I know that my rate is decreasing. So I'm going to replace dH dt with -1 root h and just see what I get for my result. If you look, all my h's cancel out. All I'm left with is 1 over 200. That is clearly a positive value. So a positive second derivative means my h prime, or my rate of change of height, it must be increasing because the slope of my first derivative is positive. So therefore, my first derivative must be increasing. Okay, next page. Let's do an extended right triangle problem. And this one is going to cover Pythagorean theorem. This one will cover area of a triangle. And this one will also cover trig. So okay, person X and person Y are walking on straight streets that meet at right angles. Y travels south, approaches the intersection. X travels east, moves away from the intersection. So one thing to make note of is that here, all three sides of the triangle are changing. It's not like the ladder problem where the hypotenuse is constant. In this case, as y is moving, as x is moving, we can imagine the triangle, all the dimensions of the triangle are changing. And then make a note of the fact that we expect this length to be decreasing, and we expect this length to be increasing, not because of direction, but because the triangle dimensions are decreasing and increasing based off the way it's drawn. Okay. Find the rate at which the distance z between person x and y are changing when y is 10 and x is 20. So let's focus on part A first. So part A, start with x squared plus y squared equals z squared. Find your derivative. Every variable gets impacted by time. And then see if you can assign all 6 variables that's going to show up from your derivative. I want you to try this on your own first. Take note that dy dt is -2 and dx dt is a +1. We have x is 20, y is 10. Pythagorean theorem can get us to z. And then we're trying to solve for dz dt. So we have 5 out of the 6 variables accounted for. So put them back into your equation and then solve for dz dt. Yes.
So
it's positive because that value is growing over time.
okay. So
dy dt is negative, right? But x and y will always be positive, yeah. But depending on what's happening to that length, then you're going to decide whether that rate is positive or negative. Now, this I know this feels like a little bit of a strange answer. The rate being 0. This is just a moment in time when it happens to be that z is probably changing from increasing to decreasing. So we caught it at that moment when the rate of change is 0. But we know it's not like the ladder problem. I think any other time other than this, the rate of change is going to be either positive or negative, because as y is moving and as x is moving, we expect the hypotenuse to be changing. But I think it's just at this moment in time, it's going from increasing to decreasing. So it's only at that moment in time where it's 0 meters per second. Any other time, it's probably not going to produce that. It's not like the ladder problem where it's always 0. It's just a moment in time when it's 0. Okay, any questions with part A? Okay, part B, it's asking for the rate of change of theta. Now, I will draw this diagram for you. I'm not going to, because it's kind of hard to know. It's like, okay, where's theta? It doesn't specify in the word problem where that angle is, but it's never at a right angle. So it's either one of these two. So if I'm going to ask you a question about rate of change of theta, the diagram will be drawn for you, or it'll be very specifically described in the problem, so you know exactly where to put that theta. So our first job is to figure out which trig function to use. So sometimes, so there's two ways. One way is where you're forced into a trig equation because there's only a limited amount of data in the problem, and you have to choose either cosine, sine, or tangent because you don't have information about the third side. The other option is where you have all 3 sides available, and you can choose either sine, cosine, or tangent. If it comes down to that, then typically we like to target a side that's a constant so that we can avoid quotient rule. But in this case, all 3 sides are moving. So I like to involve tangents, but you could use z for sine, cosine, or tangents. So in this case, because we have all 6 values, we could use any trig function, but just so that we can stay together, use tangent for now. But if you really want to, you can choose other trig functions, and we should all still get the same answer. But let's just choose tangent for now. We have all the data that we need, but the y over x forces us into quotient rule because we have 2 variables. There's no way to avoid quotient rule here. So we're going to build the derivative. Every variable is going to get impacted by time. So tangent theta becomes what?
Theta, d theta.
Good. d theta dt. And then go ahead and build your quotient rule on the right side, f prime g minus f g prime all over g squared. Okay, everybody okay so far? So we're looking for d theta dt. All this is pretty straightforward, right? We have all the data from part A that we can fill in. But the biggest trouble that students have with these trig problems is understanding that you're not replacing theta, you're replacing the entire trig function. So in order to replace that, you're going to draw a second triangle, fill out all the sides of the right triangle, and then find the secant of theta for that right triangle. So you're going to be replacing this with a ratio. And once you do that, then it's just a matter of combining all your fractions and trying to get it down to an answer. So that's the biggest trouble that students have, knowing what to do with that secant theta. A lot of students want to figure out what theta is, and that ends up down a dead end. So make sure that you understand you're trying to find a replacement for that trig ratio, not the theta value. So we can fill out our triangle accordingly. This is a moment in time, so we can use all the data from part A to build our right triangle, and then we're trying to find the secant of that theta. Secant is the reciprocal of cosine, so secant is hypotenuse over adjacent. I'm just going to reduce it so that it's easier for me to clean up. So I'm just replacing all the values I see with the data from part A, and then I'm just trying to do some cleanup, trying to get d theta dt by itself. If you don't reduce, it's fine. I just want to see d theta dt by itself with all the numbers on the right side, and then your units of measure, it's never degrees, it's always radians per time unit, in this case, radians per second. Okay, part C, find the rate of change of the area of a triangle. So based off of the variables that we've created for part A, what's the area of a triangle? 1/2 xy, yep. And if I want to find the rate of change or area, I got to find the derivative. dx dt will show up, dy dt will show up, but we got to make sure we go through what? Product rule, yeah. So go ahead and build your derivative using product rule, and then all the data you can reuse from part A. Our units of measure, area is two-dimensional unit, so it's got to be meters squared. Time is seconds, so meters squared per second. Okay, we worked through the packet, but it doesn't include all the things related rates-wise. So again, the bottom of this page indicates all the types of problems we need to be responsible for the quiz. We have a little bit of time left over. Can we look at page 14? This is a cone and cylinder problem that we skipped over. So page 14 from your packet. Okay, so this problem looks like a lot, but it's kind of breaking it down into parts here. So you're just focused on the cone for part A. And then when you get to part C, then you can worry about the cylinder. So it's kind of breaking it up into parts here. So let's read the problem here. We have water is draining from a tank, from a cone tank. The dimensions are provided here, 12 feet tall, diameter is 8 feet. And the water is draining into a cylindrical tank with an area of 400 square feet. The depth is the rate of change is changing at a rate of change of h is h minus 12. Part A, write an expression for the volume of water for the cone tank as a function of h. So just treat it like the first part of a cone problem where you're going to build your proportion and you're trying to get rid of r and you're trying to get everything in terms of h. So part A is not even asking for the derivative. It just wants us to create a volume equation so that it's nice and clean, so that part B, we can jump into the derivative process. So start with building your proportion, your similar triangle that you're going to use. All right. What's the radius of the tank? 4. And what's the height of the tank? 12. Okay. So set up your proportion. Radius of the small cone is to the radius of the large cone as the height of the small cone is to the height of the large cone. It tells us that it wants everything in terms of h, so you're going to solve for r so that you can replace the r in terms of h. So this problem is just kind of helping us step through our problem here. So it wants us to get our volume equation ready for the derivative before it asks us to do anything with the derivative for part B. So now, any questions with part A? So now part B says, at what rate is the volume changing at h equals 3? So we can now find dv dt. We can go through a power rule on the right side. dh dt will show up. And then we can find replacements and try to get it down to a number. No issues with part A? Okay, so now let's go ahead and build our derivative. Pi over 27 stays. The power rule is for that h variable. Gonna do some cleaning up here. Make it pi over 9. Okay, we're solving for dv dt, but they tell us that h is changing at a rate of h minus 12. So we know dh dt is defined as h minus 12. So we're going to use that information. but H is 3, so we can replace 3 and for all the H's as well, and that should get us down to a number. The 9s, 3 squared is 9. The 9s cancel out, numerator and denominator. 3 minus 12 is negative 9. So dV dt is negative 9 pi. What's our unit going to be? Volume is, yeah, cubic feet per minute. So does it make sense that dV dt is going to be a negative value for the cone? Okay. Now, before we get to part C, what do you think the dV dt is for the cylinder? Yeah, it's going to be a positive 9 pi, right? So the rate that the water is leaving the cone is going to be the exact same rate, but positive for the tank, because tank is going to be receiving water while the cone is draining water. So there's going to be an adjustment, but dV dt will just be a positive 9 pi when we get to the cylinder tank. Okay, we'll pick this up tomorrow after our 5.1 lesson. No homework tonight, but your quiz is Friday, so start looking over your notes for your Friday quiz. I'll send out a reminder tonight that if you want to print out your packet on my website. But otherwise, come prepared with a spiral notebook so you can take notes in your packet.
It's okay. I'm talking about upstairs. Wait, if you go really early? Okay, yeah, now you're not funny. Bro, it's so no class. You're like,
I see how you do that. No, I did it. I said I didn't do it.
Oh, you're laughing. Dude, yeah, that was so like, bro, yeah, that's great. There's no issue. I was like, bro. Yeah.
good, okay, white.
Thanks, guys. Have a great day. See you tomorrow. Bye. Thanks.
Yeah, and that, like.
Awesome.
I don't even think she knew it was. I think it was like.
I'm only the ones that are like, everything else. Do one of these later versions. Well, plus the
Yeah. Thank you, Mr. Hayden. Have a good day.
Let's see how you do it. Then what's the other steps?